Hi everybody. I'd like to keep on schedule with our materials, so I'm just recording the lecture for today so that you guys can watch it on your own, and we can start with week 8 stuff next week. Today we're going to introduce two new random variables, the geometric random variable and the related negative binomial random variable. We're going to go over a few examples. We'll talk about some formulas for things like expected value, variance, the moment generating function, etc. But hopefully by the end of this video you'll have a good sense of how the geometric and negative binomial random variables work and in what situations we should apply them. Like the binomial random variable, the geometric random variable is also based off of a Bernoulli trial. Alright, so remember our Bernoulli trial is essentially just the random variable that models a coin flip where the coin is not necessarily fair. The idea behind a geometric random variable is we're going to repeat a Bernoulli trial, but we're not going to repeat it a fixed number of times like with the binomial random variable. Instead, the idea is to repeat a Bernoulli trial until we observe the first success. And what x, our geometric random variable, is going to do is it's going to count the number of repetitions that we required to observe that first success. All right, so you might think of this, in the coin flip example as being like, I'm going to flip a coin until I finally hit a head. And what the geometric random variable is going to do is keep track of what round that first head actually appears. So I might flip and get a tail, and then finally on the third flip I get a head. So x, this geometric random variable, would take on the value of 3 because that's the round or the number of repetitions we required in order to first observe the head. All right. In the more general setting, we're going to be looking at how many repetitions are necessary for the first success. I should say that some sources will define the geometric random variable as the number of failures required to observe the first success, and it's very straightforward to kind of move from our definition, which involves the number of repetitions necessary, to the other definition, and I think I put a little bit of that into the reading. But anyways, so if we assume that x is the geometric random variable, the only parameter that gets involved here is the probability of an individual success. So what's the probability of a head on the coin that we end up flipping? All right, so we call this p, and this is consistent with our binomial random variable notation. So p is the probability of success on an individual trial. All right. And q, also consistent with our binomial random variable notation, q is just going to be the probability of failure. So this is 1 minus p. Now, generally speaking, if we're counting the number of repetitions necessary to observe the first success, right, we have to have at least one repetition in order to see it as success. So the first element in our space is 1. And then we could have 2, 3, 4, and technically this would keep going on forever, right? So we've seen a space like this before. Now, if we think about how you would end up working with the PMF, we can kind of derive how this ends up working. Let's take, for example, trying to compute the probability that x is equal to 3. So what this would mean in terms of a coin flip is we would get essentially the event tails, tails, heads. And if we think about how this would work, we would have a failure, and then finally the head would be in that final round. And so this ends up being q squared times p. Right, so in the general case, if we're looking at the probability that our random variable is equal to little x, what you would get is a string of failures, specifically x minus 1 of these, and then in the final round we would have our success. So we would have q x minus 1 times p, and that's where we get this PMF formula. So let's take a look at an example that uses this geometric random variable. Okay, so let's suppose that the pass rate for the P exam of the Society of Actuaries is roughly 41%. So for any given individual, there's a 41% chance that they'll sit for the exam and actually pass. If we assume these are the odds of a candidate passing each time, right, what is the probability it takes 3 or fewer attempts to pass the exam? Right, we make a little note here. Implicit in this design, in the design of this question, is the fact that the first success marks the end of the repetitions, right? So this won't be the binomial random variable because if we pass on the second try, we wouldn't try it again on the third, right? So the first time that we actually pass the exam is going to be the end of the repetitions that we use. All right, so try to convince yourself why this type of situation here, right, taking an exam until we finally pass, really is different than the binomial random variable where you're going to repeat a fixed number of times, regardless of where your successes and failures occur. All right, so let's think about how we would do this. First thing we want to do is convince ourselves that this is the geometric random variable. So we do have more or less a coin flip, right? We're going to sit for each individual flip. We'd be sitting for an exam. And if we pass, that's one option. If otherwise we don't pass, so there's kind of a success-failure type of relationship here. And as we mentioned before, we're just going to keep taking this exam until we finally observe a success, right? Until we finally pass the exam. All right, so this is an example of a geometric random variable. And in order to start working with this, we need to figure out what our probability of success is. Now, in our case, we define a success as essentially passing the exam, right? And we know that the pass rate for the P exam is 41%. So what we're going to use here for our parameter, little p, the probability of success on any given sit, is going to be 41%. Okay? Now, according to the previous slide, this means that our PMF is going to look like the following. 0.41, that's the probability of success. This occurs in the final round. And then 0.59 to the x minus 1. These are the x minus 1 failures that we experience before our final pass. Now, in our case, what we want to know is what's the probability that it takes 3 or fewer attempts, so x is less than or equal to 3, in order for this to work, right? In order to pass the P exam. All right, so keeping in mind the space of our random variable, it starts at 1 and then counts up. So in terms of the PMF values we need to consider, it's just f of 1 plus f of 2 plus f of 3. And then we can write out what these PMF values actually are. So this would be 0.41. And x minus 1 is 0, so we won't have a 0.49 for the first one. We'll have a 0.41 times a 0.59, and then plus a 0.41 times a 0.59 squared. All right, so one nice thing about the geometric random variables, when you have sums like this, you can factor out a 0.41. The probability of success comes out of all of them, and we have 1 plus 0.59 plus 0.59 squared, and then we would go to our calculator and figure this out. So this is approximately equal to 0.7946. Now I just do want to highlight one thing here. When you use the geometric random variable and you get these kind of sums of successive powers, it is possible and probably recommended to, if you have a large sum of these, to use your geometric sum formula. So I'm going to write out a separate example using this same random variable, and I'll show you how that works. So let's suppose that we wanted to find the probability that x is, let's say, less than or equal to 10, right? So this would involve looking at f of 1 plus f of 2 plus ... out to f of 10. And writing out our PMF, this would be 0.41 plus 0.41 times 0.59 plus etc., 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 0.41 times 0.59 to the 9th. Okay? And then factoring out our 0.41, right, we're now left with 1 plus 0.59 plus 0.59 squared plus ... all the way out to 0.59 to the 9th power. Okay? And if we keep in mind that we've got this very nice geometric sum formula, right? 1 plus x squared all the way out to the kth power. This is equal to 1 minus x to the k plus 1 over 1 minus x. Right? We can simplify this part of our geometric sum. So this would equal 0.41, and we would have 1 minus 0.59 now to the 10th power, because you have to increase, we stopped at the 9th, so you increase to the next one up, over 1 minus 0.59. And notice that 0.41 and 1 minus 0.59 are the same values, so these actually end up canceling. And this whole summation simplifies to 1 minus 0.59 to the 10th. And then there you could plug that into your calculator and get an answer. So this is about 0.99489, we'll call it. Okay. Now, using this geometric series approach, one can actually show a general formula that says, if you have the probability that x is less than or equal to c, right, this is the same as 1 minus q, right, our probability of failure, to the c power. And you should recognize this as the cumulative distribution function for the geometric random variable. Okay? And this is a very helpful formula to know because it shortcuts a lot of your computations if you can use this properly. Okay, so there are some other very nice formulas associated to our geometric random variable. First of all, the expected value of this random variable is just 1 over p, right? So if you divide, if you take 1 and you divide by your probability of success, it gives you the expected value of the number of rounds it takes to observe your first success. The variance is q over p squared, and we can verify this either by looking at the definitions for variance and for expected values, so you'd sum over your space certain things, or you could look at the moment generating function, which we can also derive. This is p e to the t over 1 minus q e to the t, and we could look at successive derivatives to find the first moment, find the second moment, and then put those together to find the variance itself. There's a little mistake in the slides, which I'm correcting here. The cumulative distribution function looks like 1 minus q to the x, and keep in mind that this is the exact same thing as the probability that capital X is less than or equal to some specific value. Similarly, the survival function is defined as the probability that your capital X is strictly greater than the input to the function. Okay, so we have these shortcut formulas, and these are going to be very important for helping us quickly compute some probabilities, which I'll show you in the next example. The other thing that I want to note here is that this geometric series formula and even the geometric sum formula, which we showed in the last example, are really important for using proofs to derive these formulas. Okay, so for the next example, I want to look into this. Same basic setup, but we're interested in what's the probability, right? So what's the probability it takes between 3 and 7 attempts to pass this exam? So if we write this out, we still have x as being geometric with a parameter of 0.41, right? And then this, of course, implies that our q, our probability of failure, is 0.59. So what we're interested in finding here is the probability that our random variable x falls between 3 and 7. And now, since we're dealing with this geometric random variable, what we want to do is compute this in a faster fashion by writing this particular probability as a difference of two cumulative distribution values. So if you think about how we might be able to do this, one option is to kind of overcount our probabilities by looking at the probability that x is less than or equal to 7. Right? And then we want to essentially just erase the probabilities that are less than 3. So we can erase the probabilities that are less than or equal to 2. And this is now written in terms of two CDF values. So we can think of this as just being f of 7 minus f of 2. So using our formula from the previous slide, we can quickly compute this in terms of the probability of failure. Now, be careful here. Make sure that you distribute your negative sign through. But what you should get is essentially q squared minus q to the 7th at the end here. So to quickly compute this probability, you just have to look at the difference of 0.59 squared from 0.59 to the 7th. This is approximately 0.323, let's call it. All right, so this is one way to do this. You could also use your survival function. Remember that your survival function is defined in terms of this is the probability that your random variable is strictly greater than the input of that function. So if we decide to do this, let me create a little space here. So if you decide to use the survival function, right, we're going to start by looking at this side first. So we want to include 3, so the x value we want to use is actually the probability that x is greater than 2, so that would make sure that we include 3. And then we want to get rid of everything that's above 7, so what we'll subtract here is the probability that x is greater than 7. And notice that when I'm working with the survival function, I use the strict greater than. So we would be able to write this as survival function of 2 minus the survival function of 7. Now this is just q to the x, so we get directly to our q squared q to the 7th that we got to using the cumulative distribution. But these are the two ways to approach this now that we have access to a nice survival function or a nice cumulative distribution function. Now our follow-up question asks for the expected value for the number of attempts required to pass this exam. Now, based on our formulas, this is pretty straightforward, right? Because we know the expected value of the geometric random variable is equal to 1 over p. And since our probability of success is 0.41, we would just have 1 over 0.41, and this is approximately 2.44. All right, so it's going to take, I mean, this is a decimal answer, right? So you can't sit for an exam 2.4 times. So the idea here is that somewhere around 2 to 3 would be the most likely number of attempts it would take to pass this exam based on this probability of success.